This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, this will be discussing principal stresses and strains in mechanics of solids. The engineering component and structures of machines or any structures is always subjected to different load conditions, which involves it may be direct stresses or compressive stresses or sometimes shear stresses, or it may be the combination of tensile, compressive as well as the shear stresses. Here we have studied the nature of intensity of shear stresses on the planes. Other than that, which are right angles to the line of action of the force are important particularly for the designing. The principal planes in a strain materials, strain means when it is subjected to tensile, compressive or shear stresses. There are three types of planes which are mutually perpendicular to each other, carry direct stresses only. That means there is no shear stresses. Out of these direct three stresses, one may be just maximum, one may be the medium, other one it may be the less. All are not all having equal in magnitude. The particular planes which are not having any shear stress on it, the type of planes are called principal planes. That is principal planes. Even though we are now discussing three types of stresses like tensile, compressive as well as the shear stresses, the particular planes which are not at all having any shear stresses on it are known as principal planes. Principal stresses. The magnitude of the direct stress across the principal plane is known as principal stresses. Here the magnitude of direct stress means this direct stress, it may be the tensile or it may be the compressive in nature. The determination of principal planes as well as the principal stresses are important in the design of various structures as well as the machine's components. There are two methods generally involving in determination of shear stresses on oblique section of a plane. They are analytical method and second one is known as graphical methods. In graphical methods, most circle is used to determination of shear stress, tensile stress as a resultant of tensile as well as the shear stresses. So first we are considering the analytical method. The determination of stresses on oblique section in the following cases. A body is subjected to direct stress in one plane. Here we are determining the stresses on oblique plane. The first one is when the body is subjected to one direct stress. It may be here tensile or it may be the compressive in nature. The second one is a body subjected to direct stress in two mutual perpendicular directions. That means if the object it is there now, here it is nothing but assume just along the x direction, sigma x and sigma x, and y direction is also there now. That is sigma y and sigma y. In this case again we have to determine what are the stresses that are acting on an oblique plane which is making an angle of theta with respect to the principal stress. That is nothing but major axis or the axis of the object. Generally, preferably it is along the x directions. The third one, body subjected to direct stress in two mutual perpendicular directions. A body subjected to simple shear stress. A body subjected to a direct stress in one plane and accompanied by simple shear stress. And a body subjected to direct stresses in two mutual perpendicular directions and accompanied by one simple shear stress. Here, these are the types of the stresses we are considering which are acting on a body. In these conditions, we have to determine what are the magnitude of shear stress as well as the tensile stress on oblique plane, which is making an angle of theta with respect to the x-axis. So, in analytical method, some conventions, sign conventions are we are assuming, like all the tensile stresses and strains are taken as positive, whereas the compressive stresses as well as the compressive strains are taken as negative now. The shear stress which are tends to rotate the element in the clockwise direction is taken as positive and anti-clockwise direction is taken as negative. So first of all I am taking the tensile stresses and strains are taken as positive means here if I take the object it is there now. This is known as that is tensile stress now along the x directions. Here because of this force the body tends to elongate in the direction of applied stress. This is known as tensile stress. For analytical method this stress is treated as a positive now. Similarly if I take the same object now, but stresses are acting in such a way that the length of the object is decreases. These type of stresses are called compressive stresses. The strain which is produced corresponding this strain is called compressive strains. These two are treated as negative according to the analytical method. Now regarding shear stress, which tends to rotate the body in clockwise directions. Here I am taking this symmetric object now. Here shear stress is there. Both are equal in magnitude and acting opposite directions. These stresses always tends to rotate the body in clockwise directions. Hence these stresses are treated as positive shear stresses. Similarly, if I take the object now, here both are acting assume these directions now. It tends to rotate the body in anti-clockwise directions. So these type of shear stresses are treated as negative. Now, stresses on oblique section of a body subjected to direct stress in one plane. Here, consider rectangular body. Here, it is considered rectangular body subjected to one single direct stress along the x directions as shown in figure. Here, sigma and sigma as shown in figure. The thickness of this object is treated as here taken as here 1 unit now. This is nothing but equal to 1 now. That is when you are taking the area, the thickness is nothing but treated as equal to 1, which is equal to the, assume this is nothing but AC is equal to the here height and thickness is equal to here now. It is B there. B is equal to 1 now. This is nothing but the area of the cross section which is perpendicular to the tensile stress. But according to our problems, H, B is equal to 1, it is equal to H is equal to L, the dimensions AC now. Okay, these are the conditions. Here we are considering the object which is having uniform cross sections but having thickness is equal to 1 unit now. Now consider the oblique section AB, here AB, which is making an angle of theta. Here measured in clockwise directions as shown in figure with respect to the x-axis now. Let N we are assuming sigma is equal to tensile stress across the section AC, because the AC is there now, this face is like a AC, and theta is equal to the angle with which the oblique section AB, makes with the x-axis, which is measured in clockwise directions as shown in figure now. Now we have to consider what are the tensile as well as the shear stresses that are acting on oblique section AB now. Now first of all we have to consider the equilibrium of the an element or which is represented here now A, B, C, and just we have write it the free body diagram for this one now. Here this is representing, here it is equal to just A, B, C now. Here the forces which are acting now, one is nothing but representing sigma, already it is there, which is toward the left hand side now. Here the resultant which is there toward the right hand side, that is resolved into two components along the plane AB as well as the perpendicular to the plane. Now we have to consider what are the magnitude of shear as well as the tensile stresses which are acting on oblique plane AB, whose resultant is equal to sigma values now. So the horizontal force acting on a face AC is equal to, we are taking just sigma into AC, because here the force which is acting on AC is equal to oblique sections, which is equal to here stress multiplied by the area required. Area is equal to AC into, again thickness is equal to unity we are taking now. It can be written as sigma into AC now. Resolve this force into two components which are perpendicular. Resolve the forces just perpendicular or normal to the section AB, because both are now just it is there now, both are equal in magnitude now. When we are taking just here now, one is a perpendicular like this, one more is a parallel now. Here, this is the directions now. That means resolving the force of perpendicular to the normal to the plane Pn. Here, this is equal to sigma. Sigma is nothing but equal to, when it is multiplied by A, it is called just a P force now. That P is equal to sigma into A now. So it can be written, resolved in two components means, here it is nothing but equal to perpendicular is there. This angle is known as here horizontal and parallel to there. This is known as theta angle now. So it is now perpendicular to there now. Hence this is known as P into sin theta. We can take this component is equal to P sin theta. This component is equal to P cos theta. So resolving the forces into two components. One is along the plane AB and one more is the perpendicular to the AB. So the normal force or perpendicular force to the section AB is given by P sin theta. It is given now. But P is nothing but equal to force, which is equal to the product of stress multiplied by the area. It is equal to sigma into AC into sin theta now. Similarly, resolve the force tangential to the section AB, which is equal to P cos theta, which is equal to sigma into AC cos theta, because the P is nothing but a force which is the product of sigma into AC and cos theta. Here, P sin theta is treated as here the perpendicular force. It is a positive because it is having the nature of tensile. Similarly, the shear stress P cos theta, which is equal to sigma AC cos theta, which tends to rotate the body in clockwise directions. Hence, it is also treated as the positive now. So, the normal stress across the section AB is equal to normal stress. Here, it is the stress is equal to P sin theta divided by the area of the cross section. Now, area of the cross section is equal to here sigma AC sin theta, it is the force already given in equation number 1 divided by the CAB into 1 now, because we have taken the unit is equal to 1 now. So from this relationship we got to sigma AC by AB is equal to AC divided by AB is equal to sin theta. Hence here sin theta and sin theta, it is equal to sigma sin square theta, which is equal to sigma into sin square theta is equal to, it can be written as 1 minus cos theta by 2 or sigma by 2 minus of sigma cos theta by 2 now. Similarly, the shear stress or the tangential stress, that means which is acting along the plane, is given by the force is equal to sigma AC into cos theta divided by again AB, that we are taking AB, it is equal to sigma. Here AC by AB is equal to sin theta, and cos theta already there. We can take it as cos theta, which is equal to sigma by 2 into sin 2 theta. This is the tangential stress that is acting along the plane now. When sin theta is equal to 1 means, that means 2 theta is equal to, we require n 90 degrees, or theta is equal to 2 theta is equal to, we require 90 degrees. That means here theta is equal to 45 degrees now. That is the maximum stress obtained when sin theta is equal to 1 or 2 theta is equal to, it may be 90 degrees or maybe 270 degrees, or theta is equal to 45 degrees or 135 degrees. At this inclination of the plane, the shear stress is the maximum, which is equal to half of the direct stress now. Therefore, the magnitude of maximum shear stress is the half of the tensile stress, but when the inclination of the oblique plane is equal to the 45 degrees or 135 degrees, the resultant stress may be obtained by using the relations under root of sigma n whole square plus tau whole square. Okay, based on these equations, we are taking one problem now. A wooden bar is subjected to a tensile stress of 5 megapascal. What will be the values of normal and shear stresses across the section, which makes an angle of 25 degrees with the direction of tensile stress now? Okay, the given data in the problem is the tensile stress is equal to sigma 5 megapascal. Because it is a nature is the tensile, it is treated as a positive in nature. The angle made by this section with the direction of tensile stress is equal to theta is equal to 25 degrees is given. According to the previous derivations, the normal stress across the section AB is given by sigma n. It is equal to sigma by 2 minus of sigma cos 2 theta by 2 now, which is equal to here 2.5, because sigma is equal to how much value is given? 5 megapascal is given. That is 5 by 2 is equal to 2.5. Here sigma is equal to 2.5 into cos 50 degrees, because theta is equal to 25, 2 theta is equal to 50 degrees now. So which is equal to 2.5 minus of 2.5 into cos 50 is equal to 0.6428, which is equal to, and doing the calculation we got to 2.5 minus 1.607, which is equal to 0.89 megapascal. This is the normal stress that is acting on the oblique plane AB now. Similarly, the shear stress across the section is equal to tau is equal to sigma by 2 into sin 2 theta, which is equal to here sigma by 2 is equal to 2.5 and 2 sin theta is equal to sin 50 degrees, which is equal to 2.5 into sin 50 is equal to 0.766, which is equal to 1.915 megapascal. Okay, this is the tensile stress, shear stress that is acting on a oblique plane, which is making an angle of 25 degrees with the direct stress now. Okay, this is the, just in this section we covered what is the types of stress, types of planes, what is the principal stress, what is the principal plane, and what are the stresses that are induced when an object is subjected to a tensile single direct stress on oblique plane, which is making an angle of theta as shown in this figure now. Okay, thank you. These are the textbooks this are followed for collecting these materials. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.